All right, so in this video, I'm going to talk about a player's beliefs, mixed strategies, and expected payoffs. So it is important for players to think about each other's strategic choices. So we use the term belief for a player's assessment about the strategies of the others in the game. So for example, let's consider the prisoner's dilemma game in which each player chooses between strategies confess or deny. So player one may say to himself, I think the other guy is likely to play strategy D, or I think the other guy will surely play strategy C. These are two alternative beliefs that player one could have. But unfortunately, a statement such as, I think the other guy is likely to play strategy D is somewhat ambiguous. So because we aim to model decision-making mathematically here, we'll need to a precise way of representing a player's beliefs. So we're going to use probabilities. So let's look at beliefs. So let's continue with the prisoner's dilemma game, and suppose we let P represent the likelihood that player one thinks the other player will select strategy C in this game. And so formally, P is a probability, a number between 0 and 1. So where if P is equal to 1, then the player one is certain that that player 2 will select strategy C. And if P equals to 0, that means player 1 is sure player 2 will not choose C. So the probability that player 1 believes the other player will select D is 1 minus P. So 1 minus P is the probability that player 1 believes that player 2 is going to choose D with this probability. So if let's say P equals to, let's take a number, let's say it's 1/2. So if P is equal to 1/2, then player 1 believes that the other player is equally likely to select C and D. So the numbers P and 1 minus P, so P and 1 minus P, they constitute a probability distribution over the set of strategies. So C and D are the strategies, right? So set of strategy. So you're assigning a probability of P to strategy C, and you're assigning probability 1 minus P to strategy D. So keep in mind that probability, must lie between 0 and 1. So the player 1 thinks it is possible that player 2 will play strategy C, and also thinks it is possible that player 2 will play D. So player 1 might not believe that player 2 actually randomizes, let's say by flipping a coin. It's just that player 1 may be uncertain about what strategy player 2 will choose. And so he associates probabilities with player 2's strategies. So player 1's belief may not be accurate. He could be certain that player 2 will select C, when in fact player 2 selects D. All right, so this is a general idea about beliefs. It's a probability distribution over the other players' strategies. So next, we're going to look at it a little bit more formally. So we can define belief for general normal form games. So a belief of player I is a probability distribution over the strategies of the other players. So we can denote the probability distribution as theta subscript minus I. So this is the probability distribution. Basically, it's the belief of player I against his, you can say rivals, opponents, or other players. So you can write that theta subscript minus I belongs to delta S subscript minus I, where delta subscript S subscript minus I is the set of probability distributions over the strategies of all the players except player I. All right, so let's say, just to look at it in a very simple way. Let's say we have a two-player game. So if you have just two-player game, then player I minus I is basically the other player. So let's call it J. And suppose each player has a finite number of strategies. So the belief of player I about the behavior of player J, we have just keep in mind, we are just two players, I and J, right? So the belief of player I about the behavior of player J is a function. So that function is theta J. Keep in mind, minus I, same thing as J, because we have just one player, other player. So this is player I's belief about player J's strategy, okay? So this belongs to delta Sj. So for each strategy Sj, so a particular strategy Sj belonging to Sj of player J, theta J of Sj can be interpreted as the probability that player I thinks that player J will play strategy Sj. Okay. So as a probability distribution, theta J has the property. So let's look at the property. So theta J of Sj is greater than equal to 0 for each Sj belonging to Sj. And summation, so sigma Sj belonging to Sj of theta J of Sj is equal to 1. So this is just a formal notation. It's telling you the last expression I have written, the sigma Sj belonging to Sj. So you're summing up basically probabilities. So basically other players' strategies, whatever the number of strategies other players have, you're assigning, the player, I is assigning some probabilities. What is the likelihood that player J is going to play this particular strategy, right? So the idea is that when you add up all these probabilities, they must be equal to 1. So that's what this means here. All right, so next, let's look at mixed strategies. Okay, so a mixed strategy. So we're going to look at a mixed strategy. So mixed strategy is related to, beliefs. A mixed strategy for a player is the act of selecting a strategy according to a probability distribution. So for example, if a player can choose between strategies U and D, so we can imagine her selecting U with some probability and D with some probability, right? So U is chosen with some probability and D is chosen with some other probability. So it's very similar to beliefs, as you can see. So she might flip a coin and select U if the coin lands with the head up, and D if the coin lands with the tail up. So more formally, a mixed strategy is just like a belief in that they are both probability distributions. So we'll denote a generic mixed strategy of player I by this letter sigma I, and sigma I belongs to SI. So set of strategies SI. So sigma I is a probability, over the strategies of player I. So this would be delta SI. Okay. So just to make sure that sometimes we'll call a regular strategy a pure strategy to distinguish it from a mixed strategy. So keep in mind that the set of mixed strategies includes the set of pure strategies, each of which is a mixed strategy that assigns all probability to one pure strategy, right? So here we have probability of, up is P and probability of playing down is 1 minus P, but if P equals to 1, then 1 minus P is 0, meaning player is certain to play up, right? So that's a pure strategy. There's no mixing here between the pure strategies. So if a player uses a mixed strategy and or assigns positive probability to multiple strategies of the other player, then this player cannot expect to get a particular payoff for sure. So we can extend the definition of a payoff function to mixed strategies and beliefs by using the concept of expected value or expected payoff. Expected payoff or expected value. So when player I has a belief, let's say theta minus I, about the strategies of the others and plans to select a strategy SI, then her expected payoff is the weighted average, payoff that she would get if she played a strategy SI and the others played according to her belief theta sub minus I. So you can express this expected payoff mathematically. So it's UI of SI given theta minus I is equal to sigma S minus I belonging to S minus I theta minus I of S minus I times UI of SI and S minus I. So basically you're saying here that the expected payoff for player I when she plays strategy SI, her strategy, given her belief about other players' strategies, right? So she's guessing what other players will choose, right? And assigns a probability on that. So then it is basically, probability which is her belief about other players' strategy here, right? On a particular strategy, the rivals play S minus I, multiplied by the payoff that is assigned to strategy SI given the rival strategy S minus I. So let's try to understand it. This mathematical definition of expected payoff by considering a simple game. So let's look at a game here. So let's say the game is a 3x3 normal form game. So let's write it down here. So the game is a 3x3 game. All right, so here we have player 1 gets rows, player 2 gets columns. All right, so let's say player 1 has 3 strategies: play up, center, or down. And player 2 has also 3 strategies to play the game: left, middle, and right. And the payoffs are 8 and 1, 0 and 2, 4 and 0. And here 3 and 3, 1 and 2, and 0 and 0. Over here 5 and 0, 2 and 3, and 8 and 1. So each, in each cell, the first number belongs to player 1. That's player 1's payoff, and the second figure belongs to player 2. All right, so we want to find out the expected payoff of player 1 when she plays up or center or down, right? So let me show you how you can calculate expected payoff. So first we need to know what are the beliefs of player 1 about player 2's strategies, right? So let's say player 1 believes with probability 1/2 that player 2 will play strategy L, okay? And with probability 1/4, she believes player 2 will play middle, and with probability 1/4, she believes that player 2 will play right. So this is her guess, basically, and it's a conjecture what player 2 might do. So there is a 50% chance player 2 will play left, and 25% chance player 2 will play middle or right. So this is player 1's belief. This is her guess, basically, about player 2's strategy, right? So she's forming this in expectation here. So now, given this, we want to so you can write it, notation wise. The one we have developed before, basically, we're saying player 1's belief about player 2's strategy. So theta 2, which is theta sub minus I, right? So other players, player I's belief about other players' strategy, which is theta minus I. So we have just 2 players, 1 and 2. So player 1's belief about player 2's strategies, right? So theta 2 of strategy SI, which is L here. So strategy is L, and that is 1/2. Similarly, you can write player 1's belief about player 2's strategy. Middle, the belief is that she's believing that player 2 will play this with 1/4. And similarly, you can write for right the strategy R, which is also 1/4. So you can always write in a shorthand notation, player 1's belief about player 2's strategy is 1/2, that's for L, 1/4 for middle, and 1/4 for the right. So you can always write it like this. All right. So So now we know what our player one's belief about player two's strategies. So next we can use this to calculate expected payoff. So expected payoff, if you remember the expression, so player one, let's say we want to find out what is player one's expected payoff if she plays up, right? So U1, so expected payoff of player one from playing up, given her belief about player two's strategy. So her belief about player two's strategy is theta 2, right? So that is equal to, keep in mind that we are looking at what is the probability that player 2 will play L, middle, and right, and you are going to multiply those with individual payoffs, right, for player 1. So here, player 1 believes player 2 will play left with probability 1/2, and if she plays left, then player 1 will get 8 as payoff. And player 1 believes player 2 will play middle with probability 1/4, and in that case, if she plays up, she's going to get a 0, right, payoff of 0. And then she believes that player 2 will play right with a probability of 1/4, and if she plays up, then she's going to end up getting 4. So now we need to add these up. So the expected payoff of player 1, given she plays up, and her belief about player 2's strategies, as given by this over here, is equal to, so 1/2 times 8 is 4, plus 1/4 times 0 is 0, plus 1/4 times 4 is 1. That sums up to 5. So this is what we mean when you add up, everything. So her expected payoff from playing up is 5. This is what she expects to play, expects to get when she plays up, given her belief about player 2's strategy. Now, just to make sure that you understand it, so we can do another exercise like this. So let's say you want to find out what is the expected payoff of player 1 when she plays D. Okay, so let's use a different color here. So let's say she plays D. Okay, this one. So we can calculate it in the similar fashion. We already have the beliefs. So let's write it down here. So expected payoff for player 1, given she plays strategy D, and her belief about rival strategy is given by this theta 2, which is this basically, right? 1/2, 1/4, 1/4. So in that case, we know she will get, so player 2, if he plays L with probability 1/2, and player 1 chooses D, she'll end up with 5. And if player 2 plays middle with probability 1/4, and if player 1 chooses D, she's going to get 2. And if player 2 plays R with probability 1/4, then player 1 will get 8 by playing D. So this will add up to, so 5/2 is 2.5. So 5/2 is 2.5 plus 2/1/4. So 2 times 1/4 is 0.5. And then 8/4 is 2. So 2.5 plus 0.5 is 3. 3 plus 2 is 5. So here also, C will get an expected payoff of 5. All right. So, and what would be the expected payoff if player 1 plays C? So you can do the math here. So let's say 1/4 times 3, 1/4 times 3 plus, sorry, 1/2 times 3 because player 2 plays L with 1/2, and plus 1/4 times 1, and plus 1/4 times 0. So in that case, the expected payoff would be 1.5, 3/2 plus 1/4, which is 0.25, plus 0. So 1.75. So in this case, expected payoff is 1.75. All right. So this example illustrates how you can calculate expected payoff of a player from a certain strategy once he has a certain belief about the other player's strategies.